Welcome back to today's class on chemistry practicals. Okay, as you can see on the board, we have experiment 2. The title of this experiment is separation of mixtures, and of course the objective, which is what you're looking for to achieve in the lab, is to separate heterogeneous mixtures based on the chemical and physical properties of each component. Now this class is going to be divided into subsections. Now the first section would be me trying to explain these practicals to us so that at least you have an understanding of what the experiment is all about. Now the second section would be the procedures, okay, the steps, what and what you need to do. And the third one would be calculations, okay. So during the class you have any question, please do well to drop it on the comments. Myself or somebody else will actually attend to your question. Now, before I proceed, please, every lab, every practicals, your manual will always have space for your report sheet, or more like a worksheet. Now, you have to put this down, okay? Now, experiment 2, title of the experiment is separation of mixtures. The objective is to separate heterogeneous mixture based on the chemical and physical properties of each component. Now, do not forget that you must put your dates, right? Make sure you put your dates, okay? So your apparatus, I said apparatus and material. Now, this may not really be complete, but when you get to the lab, whatever apparatus, equipment you're going to be making use of, please make sure you add it here. Now, the material covers the water, HCl. If you have reagents, let me first of all explain what this practical is all about. Now, if you take your mind back, matter can be divided into two, right? We have pure matter and we have impure matter. Okay, now for the pure matter, these are substances that are very pure, free of impurities. We have the elements and we have the compounds. Now, the impure matter, we have the mixtures. Mixtures are basically combination of two or more compounds, all right, in such a way that once you form a mixture, each component retains its property. We have two types of mixtures. We have homogeneous mixtures. We have homogeneous and we have heterogeneous. Now the key word here is homo and hetero. Homo simply means same kind, right? Now hetero means different kind or different phase. Example of homogeneous mixture is, for example, solution. When you add salt inside water, all right, the salt will be dissolved inside the water such that you're not going to be seeing a demarcation. You're just going to see water, one phase, right? Air is a homogeneous mixture because air comprises of different compounds or elements. Oxygen, nitrogen, carbon dioxide, noble gases are all present in air, but air is actually if you look at air, you cannot tell whether nitrogen is present or whether this is present. They have the same phase. But when you talk about heterogeneous mixtures, we're talking about a kind of mixtures that when you look at it, you can actually see demarcation, or they are not in the same phase. For example, fuel and water, right? If you pour a petrol inside a gallon of water, you're definitely going to see demarcation, right? The one that is more dense, which in this case will be water, would be at the bottom, and the less dense will be on top. So there is a demarcation. They are not in the same phase. All right, so the mixture in question we're going to be looking at would be, right, from this experiment, the mixture will be combination or will comprise of aluminum oxide, calcium carbonate. So these are the mixtures we look forward to separate. And then the interesting part is that they are all in a solid form, in a powdery form, but their particle size are not the same, okay? Just like when you're mixing gravels and sand, you can actually tell that they are not uniform because the size of the gravels or the stones will be bigger than that of the sand. So you could tell, yes, they are mixing together, but they are not in the same uniform phase. Now let me actually put your mind to test a little bit. It's just a little experiment to help us understand what this experiment is all about. Now let's say, for example, let's say we have these two mixtures. I'm using salt, our normal table salt, because it's something we can relate to, and I'm using sand. So imagine a case where you're asked to separate salt from sand. Now, if you use filter, it's definitely going to stress you out because there is no how you're going to do it. Salt and sand are almost the same size, particle size, Okay, so the best thing you're going to do, you're going to just try and be logical. First thing first, you say, okay, fine. Since I cannot separate salt and sand using sieving, right? What I'm going to do is I'll add water to this guy. So I'll say, I will now add water to this plus water. If you add water to this, all the salts present in the sand, all the salts present in these mixtures will be dissolved in water. Remember, salt dissolves in water. All right, that is why if you put a salt inside a cup of water and you turn it, it gets dissolved inside the water. But if you put sand inside water, it doesn't dissolve. So once you add water to this mixture of sand and salt, all right, all the salt dissolve. So what you're now going to have is going to be salt solution plus sand. All right, so now you're going to have salt solution, that is water and sand. Now that water, if you test it, is going to be salty. So the salt you were seeing that was whitish, the crystals, right? The moment you added water, it dissolved inside the water. So you now have water salt solution in form of water and sand. So from here now, you're going to filter, you're going to subject it to filtration using filter paper. Now once you actually subject this guy to filter paper, the water will be separated from the sand. So you're not going to have sand on top, that is the residue, and then inside the flask or whatever we have salt solution. So by this we have separated the salt, the sand from the salt. Now, but you notice that this sand would be wet because water had touched it. So for me to actually get pure sand, I will now dry it. Right? Now for me to now get salt, I'll now subject this guy to evaporation to dryness. Now this process, right, as you're heating it, you're stirring it, all the water will escape, right, and then leave behind salt. That is why if water should gain access to your salt, most of the times we put it on top of our, pot to allow the water to evaporate. So this is just basically to, prepare our minds to what we're going to be doing in these practicals. Majority of us, almost everybody can relate to this, right? So when I say add water to the real experiment, you should understand why we are adding water, because we want to dissolve a compound that is soluble in water, right? So stay put and see how we're going to do it. So let's look at the procedures of this experiment. Procedure 1 says, weigh a clean, dry 150 ml beaker and record the weight in your notebook as outlined on the data sheet. All right, so I'm going to be using data values from what they got last year in the lab. So all of this, I'm going to be filling it, the place that needs to be filled. All right, so please take note that the values were what they got last year in the lab. So you're not meant to transcopy that into your manual. Okay, so you're meant to carry or conduct the experiment. All right, so this value is just to guide us so that we can carry out our calculation. So they say weigh a clean, dry 150 ml beaker and record the weight in your notebook as outlined on the data sheet. Obtain a sample of the mixture, add it to the beaker and weigh the beaker and sample. Now what they are saying first is that first you're going to bring a beaker empty and you weigh this. Whatever the answer gives to you, you come here and you record it. Now that same beaker, right, you should obtain the mixture. Remember, the mixture is basically, a crystal or a solid form that is comprising of aluminum oxide, calcium carbonate. Now this is very similar to the mixture of sand and salt I gave us earlier. Now copper sulfate is a salt. Take note of that. This copper sulfate is a salt. All right, so that same pattern where we added water when salt was mixed with sand so as to remove the salt, we are still going to apply that same concept here. That was why I had to give us that illustration earlier. So the sample is a mixture of these three compounds put together. So what they said is, after you have weighed the beaker, whatever the answer gives you when the beaker is empty, you put it here. Now the next thing you're going to do, class, is to add the mixture here, right? So here you come back and you transfer the mixture. inside that same beaker and wait. So that's why they said obtain a sample of the mixture. You don't really have to obtain it. They will give it to you guys in the lab. Obtain a sample of the mixture, add it to the beaker and weigh the beaker and the sample. So once you've added it to this beaker, you're going to reweigh this guy, the beaker and the sample. So whatever the answer gives to you, you come down to this first part and you record it. Okay. So let's see the values we got for that. 0.75 grams. So for this guy, we got 52.78 grams. Now procedure 1 is done and dusted. Okay. Procedure 2 says add 50 ml of distilled water to the beaker and stir. This same beaker that contains the mixture, So they said add 50 ml of distilled water to the beaker and stir with stirring rods for several minutes. What is the purpose of adding water? Remember I said you have 3 mixtures: aluminum oxide, calcium carbonate, and copper sulfate. Now copper sulfate is a salt, just like the normal salt we have, right? That's your salt in the kitchen. If salt comes in contact with water, it dissolves inside the water. So we want to actually dissolve the entire copper sulfate. That is why they are asking us to add water. Okay, so now you come here. So let's put this guy here. Now this is a beaker and the sample is inside: copper sulfate, aluminum oxide, and calcium carbonate. Now you're asked to add 50. They said add 50 ml of distilled water to the beaker and stir with stirring rods for several minutes. Now, why are you stirring it? You're stirring it so that all the salts, that is the copper sulfate that is present inside of this, can get into the water, right? Just like, for example, if you want to drink tea, you drop sugar inside your water, you stir with a spoon. Why are you stirring it? Because you want the sugar, all of them, to get dissolved inside the water. So the moment you add 50 ml to this beaker, your sole aim is you want to dissolve copper sulfate. Copper sulfate is a salt. So once it comes in contact with water, it gets dissolved inside the water. So if you take out the water, you're taking out the copper sulfate as well. Okay. So now they went ahead to say allow the mixture to settle and decant the liquid into a second beaker. Now remember, once you add 50 ml of water to this guy, right, all the copper sulfates get dissolved inside the water, such that if you actually pour out the water, you're pouring out the copper sulfate. But there is an interesting part here. The moment this copper sulfate comes in contact with water, the water color changes to blue, right? So take note of that. Once copper sulfate comes in contact with water, the water color changes to blue. So the moment you add water to this and you stir it, you actually notice appearance of blue color. The appearance of blue color indicates the presence of copper sulfate being dissolved inside the water. So once you decant this guy, so you have inside another beaker or another container. So what you're now going to have will now be copper sulfate solution. But once water comes in contact with this copper sulfate, it now becomes .5H2O. So this is copper sulfate pentahydrate. That's water of crystallization. That simply means is that I can always obtain the salt back, right? Crystallization, water of crystallization means that a crystal has water inside of it. So you can actually take away the water and regain back the crystal. So then we have another beaker. We have another beaker that contains aluminum oxide and calcium carbonate. But it is not possible for all the copper sulfates to be dissolved in this 50 ml at once. So to be on a safe side, you have to introduce more water. And look at what the manual says. The manual says, add 55 ml more of the distilled water to the solid. Remember, we added 50 ml at first to get the copper sulfate dissolved into the water, and then we decant, having this beaker that has the water and the salt, which is blue color. This will be blue in color. And we have these other parts, which presumably it's having aluminum oxide and calcium carbonate. All right. So what we are going to do next is that they said you should add 55 ml more. They said add 55 ml more of distilled water to the solid. Stir for several minutes. and combine with the first liquid. That means if you actually add 55 ml of water here, apparently there will still be some particles of copper sulfate that did not dissolve totally. So they believe that this first 50 ml was not enough to actually dissolve this entire copper sulfate. That is why they now ask us to put another 55 ml. So if you put another 55 ml, you're meant to stir, right? Apparently, if there is any copper sulfate present here, you're going to notice blue color. So whether or not you notice blue color, transfer the water back to this other beaker that already has copper sulfate, right? So how many times have we added water now? 2 times. Now, they now said, repeat the addition of 25 ml. So what they simply mean by repeat is that after putting 55 ml here, you actually remove the water, decant the water into this first container, right? So you still come back to this same flask, a beaker. You still come back to this guy and add another 25 ml. So this last 25, that is why they say repeat. Repeat simply means you add water to this, stir it, decant it back into this first one. So you're going to add water 3 times. The first one is to capture majority of the copper sulfate, convert them into solution. Then you decant. Decanting simply means pouring out water in such a way that the solid at the bottom of your cup or whatever test tube beaker remains, right? And then the water transfers to another beaker. So this is what we have. And the leftover, which are the solids, which will be at the bottom. So we added 55 ml again to capture any remaining copper sulfate, right? The water, and still shake it, decant it back into this first one, right? Add another 25 ml to that same solid, shake it, and decant it back here. Okay, so procedure 2 is done and dusted. But listen to what they said. They said until the blue color of copper sulfate is completely removed from the remaining solid. So it simply means that once water comes in contact with copper sulfate, the water becomes blue in color. So the moment you cite any blue in color in any of this, it simply means that copper sulfate is still present. So you must continue adding water so that you can remove the entire copper sulfate. Okay, so that is what procedure 2 is all about. I believe we understand what this procedure 2 is about. Now let's look at procedure 3 very fast. Procedure 3 says, weigh a clean, dry, evaporating dish and record its weight. So this is where we're going to record it. So like I said, I'm going to be giving us the value of what they obtained last year in the lab. Okay. Now, after weighing the dry and clean evaporating dish, now the next thing they said is then slowly add 30 ml of 3.0 molar HCl into the remaining mixture. Now, first thing first, last year, this was what they got for the mass of evaporating dish. They got 34.39 grams. Then slowly add 30 ml of 3.0 molar HCl to the remaining solid mixture in the beaker. Remember from procedure 2, we started off with a beaker that contains 3 compounds: copper sulfate, calcium carbonate, and aluminum oxide. But we added water to this, and all the copper sulfates dissolved into the water, and we transferred it into another beaker, right? So what we have left now is these 2 compounds present inside this beaker. Okay, now they are asking us to add HCl to this guy. Now there is a reason for that, because if you add HCl to this beaker, HCl is going to react with calcium carbonate, right? Now once HCl reacts with calcium carbonate, it's going to convert the calcium carbonate into calcium chloride. Remember, our aim is to separate these 2 guys, but there is no better way to separate these 2 guys than converting this guy to another compound. Okay, so this procedure 3, in summary, I'm just going to explain it all just straight. But first and foremost, anytime calcium carbonate comes in contact with HCl, right, it will always give us calcium chloride, then give us CO2, which is going to evolve as a gas, and then give us water. Now, what is the sole aim of adding HCl to this particular remaining mixture? Let me explain. We have removed water we have removed copper sulfate by introducing water into that guy. So we separated copper sulfate. So what we have now left is calcium carbonate and aluminum oxide. So for us to actually separate this calcium carbonate, you're going to add HCl. Be very careful. HCl is very corrosive, right? So if you add calcium hydrochloric acid, if you add hydrochloric acid to this guy, now this is a reaction that is going to take place. All the calcium carbonate that is present in this particular mixture would be converted to calcium chloride. And once again, calcium chloride is a salt. Because let me take this in a way that you understand. I said the purpose of adding HCl to the remaining mixture, which comprises of calcium carbonate and aluminum oxide, is because HCl is going to react with calcium carbonate. And once it reacts with calcium carbonate, it's going to convert the entire calcium carbonate that is present in this mixture. We will not see it, we may not really know which of them is calcium carbonate, but this HCl knows. So once it comes in contact with calcium carbonate, it converts the calcium carbonate into calcium chloride, carbon dioxide, and water. But carbon dioxide is a gas, so there will be evolution of gas. So if you look at this beaker, after you've added the HCl, you're going to be seeing bubbles, right? You're going to be seeing bubbles on top. But that bubble simply means a gas is evolving, like a gas is going out. So when would I know that this reaction is complete? Is when I notice that there is no longer CO2 bubbling out. So the moment you notice that if you add more acid, of course, you're not going to just pack acid and pour inside, right? They said from the question you should add 30 ml of 3.0 molar HCl. You're not just going to pour the entire 30 ml. So you're going to be putting it little by little, and then you're observing. As you're pouring it out, CO2 would be evolving, all right? CO2 will be going out. The moment you stop noticing bubbles, it simply means the reaction is complete, that all the calcium carbonate has been successfully converted to calcium chloride. And do not forget that calcium chloride is a salt. So in this same container, there is water. So what we are going to have is, I'll come here and say, I have calcium carbonate and aluminum oxide. Now when you add HCl to this guy, now this is what we're going to have. In this same container, we're now going to have aluminum oxide will still be at the bottom. We're no longer going to have calcium carbonate. We're now going to have calcium chloride plus water, because CO2 will evolve. Now, this calcium chloride plus water, this calcium chloride will not be in a form of a crystal. It will be in a form of water. The water might not necessarily be much. It might just be little amount, right? Depending on the amount of HCl you poured inside here, right? So that HCl you poured inside here will now turn into water that contains calcium carbonate inside. I don't know if you understand what I'm saying. You poured HCl inside of this. This is now a chemical change. That first separation was physical. Remember, the objective is to separate using physical and or chemical. So the first one we separated copper sulfate was physical, but in this case now, this is a chemical change in the sense that you added HCl, right? This HCl comes in contact with calcium carbonate, convert the calcium carbonate to calcium chloride and water. So this stuff you added initially as HCl is no longer going to be HCl, it's going to be water. But that water, inside of that water has calcium chloride dissolved inside of it, which is equivalent to taking your salt in your kitchen and putting inside water in a cup. You're looking at water, but that water contains salt. So basically, what you're going to be seeing here is just going to be a solid at the bottom of the beaker, which in this case is purely aluminum oxide, and water, which in this case is now calcium chloride inside that water. So this time around, we can now separate again the same thing that happened in the first case when we added water so to dissolve all the copper sulfate. We saw a blue solution, we decanted it and put the water in another beaker. So this is exactly the same thing that we're going to do here. They say when the CO2 is no longer evolved, I already explained that. Once you notice that there is no longer a bubble here, that is when you know that this reaction is complete. All the calcium carbonate has been successfully converted to calcium chloride. When you notice that CO2 is no longer evolved, transfer the liquid to the evaporating dish. Transfer the liquid to the evaporating dish. Now, So this is what I'm going to do. Now this is evaporating dish. Now from this guy, remember this is now containing aluminum oxide and water, but that water, inside that water we have calcium chloride dissolved inside of it. So if you put it on top, if you transfer it inside the evaporating dish, we are about to heat it so that the water can escape, leaving us behind with calcium chloride. So when you transfer this guy now have calcium chloride and water inside the evaporating dish, and now you now have aluminum oxide standing alone inside the beaker. But this guy would be wet since water is still inside of it, little amount of water. It will be wet. There is no how it's not going to be wet. Right? Good. So it said when CO2 is no longer evolved, transfer the liquid to the evaporating dish. Wash the remaining solid free of water-soluble calcium chloride. Now, please pay attention to this. Now, there is water inside of this, so you transfer it into this evaporating dish, but there will still be, some amount of calcium chloride and water inside of this. So they now said, wash. That means you're going to add another water. Let's see if they gave us the meal that we're going to add. Yes, they said, add 20 ml of water to this same flask or beaker. First, you must have transferred the water into evaporating dish, and you have this now, right? So supposedly you come back to this guy and add 20 ml of water again. That water that is coming out, you see, transfer it back to evaporating dish, right? They now said by adding 20 ml of the seawater and stirring for several minutes, the cans they washed into the same evaporating dish. Repeat the washing and transfer to the evaporating dish. So let me break this down. I believe you already understand this. The experiment is not really that stressful. This is containing water. The water has calcium chloride and aluminum oxide. You first of all transfer the water into evaporating dish. You're going to be left with aluminum oxide. Okay, now to make sure that you're capturing all the calcium chloride, you add more water. This time around 20 ml, right? If you add 20 ml of water, you stir it and allow it. That is procedure 4 done, but we are not done yet. Procedure 4, I'm going to read out the entire procedure so that I can come back and explain. They say, place the evaporating dish containing the calcium chloride solution from part 3 on a clear triangle and heat slowly to prevent boiling. Slowly to prevent boiling. Please stick to that instruction. When nearly all the water has evaporated, reduce the flame intensity to avoid sputtering. If sputtering occurs, cover the evaporated dish with a wash glass and continue to heat slowly until the residue appears dry. Allow the dish and content to cool to a room temperature. If a wash glass is used, wash the adhered salt from the wash glass using wash bottle containing distilled water and return the wash bottle to the evaporating dish. It simply means that, remember, from part 3, we are transferred, so let's call this guy evaporating dish. We are transferred calcium chloride solution into this. They say triangle clear. All right, clear is more like something that will be generating heat, and heat it. All right, now you have to heat it slowly to avoid boiling. All right, as you're heating it, so when you notice that most of the water has evaporated, you reduce the flame intensity to avoid sputtering. So at the end of the day, after heating this guy, what you're now going to have from this guy will now be just CaCl2, no more water. Right? No more water. All right. There was water initially, but after heating it, you no longer have water. So this is now where you weigh this guy. You weigh it. Now, whatever mass you're going to have would be the mass of the evaporating dish plus the mass of the calcium chloride. Where are you going to record it? Number 3. So let's do that recording. Okay, procedure 5 now says, place the remaining beaker. Remember, we had separated calcium chloride solution. One part went into evaporating dish, which is calcium chloride solution plus water, and the other part was just aluminum oxide. Obviously, this guy would be wet because remember it was Al2O3, calcium Cl2 plus water. So when you now decant, you pour out the water inside the evaporating dish, and what is left behind is this. So there is no how this guy will not have some, it will be wet. All right, so for us to actually make sure that all the water is out, we're going to dry this. So that is now what the procedure 5 is telling us. They said, place the beaker containing the remaining solid on a wire gauge, heat slowly and stir with stirring rod, breaking up clumps of solid. Heat the beaker until the water has evaporated. Cool the beaker to room temperature, weigh and record. So now, from this, after you have actually put this on a wire gauge is basically something that is separating the heater from the flask so that it will not break this guy. Okay, now where are we going to record the mass? If you look at number 7, we have mass of beaker and remaining dry solid. Okay, so that is where we are going to record that guy. So we have 51.66 grams. That is our number 7. So we are done with the entire procedure. So what we now want to do now is calculation. So let's look at the calculation part of this. They said, what is the mass of the original sample? Now, remember that we had earlier weighed the beaker when it was empty. It gave us 51.75. And of course, we added the sample, which was the mixture, and then we added the mass, and then we added the sample, which was the mixture, and we weighed, which we got 52.78. So apparently, I would say solution. So number 1, mass of the original sample would be the mass of the beaker and sample, which is 52.78, minus the mass of the beaker when it's empty, which is 51.75, which is 1.03 grams. Just like I told them in class, this answer majority of times is always 1.0, but based on the value I used, it was 1.03, so I didn't really bother to approximate it to 1.0, so I just left it like that. So just in case you see 1.0, you'll see very correct. Okay, so here now, please, there are 2 lines here. You don't necessarily have to fill, you can use the same answer and fill the 2 lines. Now it's trial 1 and trial 2 just to avoid error. Do you get? So as to compare the error. So if you actually do it very well, there's no need of, you can put the same thing on both lines. So this is 1.03 grams. Okay, so number 2, they said percentage or percent of aluminum oxide in the sample. Now, for us to be able to get, now how do we solve this guy? We're going to solve this guy by saying this is equals to mass of aluminum oxide all over mass of original sample times 100. Now, mass of the original sample, we already know the mass of the original sample to be 1.03. Now, mass of aluminum oxide, we do not know, but from this table, we can get it. If you look at number 7, number 7 is actually mass of beaker and remaining dry solid aluminum oxide, right? So for us to get this guy, this is mass of the beaker and mass of the dried aluminum oxide. So whatever we have here, this is meant to be, please, this is meant to be 52.06, sorry. This is meant to be 52.06. Now, mass of beaker and the remaining dry solid is 52.06. Remember, mass of beaker was 51.75. So for me to now get the mass of the aluminum oxide, so I'll say mass of aluminum oxide is equals to the mass of the beaker plus aluminum oxide gave us 52.06 minus mass of the beaker when it was empty gave us 51. 0.31 grams. So for us to be able to now solve for this, so we are now going to say percent of aluminum oxide in the sample will be mass of aluminum oxide, which is 0.31, all over the mass of the original sample, which is 1.03 times 100, give us 30.1%. So this is 30.1%. Now, question number 3 says percentage of calcium carbonate. Now look at this. Please, in your manual, for us to get the value of calcium carbonate, they said, if you check your manual, you're going to see it. They say result from 5. Result from 5 times 0.9. So it simply means that for us to solve for the mass of calcium carbonate, we need to first of all solve for the mass of calcium chloride. Right? So let's do that at once. Now, mass of calcium chloride, how are we going to solve for it? Now remember from number 3 here, which is this data, you can see that mass of evaporating dish and dry calcium chloride is 34.69. And mass of evaporating dish is 34.39. So for us to be able to get the mass of calcium chloride, we're going to subtract the evaporating dish from this. I don't know if you understand. Mass of evaporating dish and dry calcium chloride is 34.69. Mass of empty evaporating dish is 34.39. So we're simply going to say mass of calcium chloride is equals to 34.69 minus 34.39 grams. Now, so the mass of calcium carbonate will now be whatever we have here times 0.9. So we now say mass of calcium carbonate equals to 0.3 times 0.9, which is 0.27. So for us to solve for the percentage of calcium carbonate in the sample, so we'll now say percentage of calcium carbonate would be the mass of calcium carbonate, which is 0.27, all over the total mass, that's the mass of the original sample, which is 1.03 times 100. So we have 26.2%. So number 4 now. Now, I don't want to really stress myself. So for us to just get number 4, that's percentage of copper sulfate, it's very simple. Since it's 100 and the sample has 3 mixtures, the sample has 3 components: aluminum oxide, calcium carbonate, and copper sulfate. So for us to actually get the value of copper sulfate, for percent of copper sulfate is going to be 100 minus percent of aluminum oxide plus percent of calcium carbonate, which is 100 minus 30.1 plus 26.2. So 100 minus 56.3. And the answer here is 43.7%. So the next session is end of experiment question, which I'll just display on the screen for you to quickly go through. If you watch this video to this very moment, kudos to you. I wish you the very best in your lab session tomorrow. Please do well to subscribe, comment, just comment something. Do you like the way I teach? Do you like the class? Just drop a word of encouragement. And also please share the video. Thank you very much. So the end of the experiment question will just be displayed on the screen for you guys to actually watch it and write it down.